Good afternoon and welcome to today's Military and Aerospace Electronics webinar, where MOSA meets COTS, Achieving True Configurability in Defense Systems, sponsored by Elma Electronic. I am Jamie Whitney, Senior Editor of Military and Aerospace Electronics. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation. But please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. To refer a colleague to today's discussion, share it on social media, or access event resources, click the icons on the left side rail of your screen. If you'd like to increase the size of the windows on your screen, click in the upper right-hand corner. Also, please be aware that today's session is being recorded and will be available on the M&AE website within the next 24 hours. You'll be notified by email when the archive is available. And let's meet our presenters for today. David Tetley, Director of Embedded Computing at Elma Electronic, and Dave Walsh, Chief Technology Officer at Parry Labs. David Tetley has over 30 years of experience in the development of hardware and software solutions for embedded computer systems in the military and aerospace market. His extensive background includes embedded software development and architecture design, specializing in real-time signal and image processing platforms for radar, electronic warfare, and electro-optical infrared systems. Throughout his career, he has led the integration of SBCs, GPUs, network switches, and digital signal processing elements, along with their associated software elements into turnkey computer systems. Dave Walsh leads research, technology, and product strategies, engineering, and capability development at Parry. He is a proven strategic engineering leader with deep experience in aircraft and ground weapon system development and MOSA across the DoD and internationally. Prior to joining Parry, Dave was Director of Open Systems for military avionics and helicopters at Collins Aerospace, where he led organizational transformation to instantiate the company's Mozark product line. Previously, he was chief engineer at Leidos, systems architect for multiple systems for Army PEO aviation, system integration lead of multiple fielded versions of the MQ-1C, and co-founder of several autonomy, automation, and expeditionary research and development products at General Atomics. And he is a former Army aviator. Gentlemen, welcome, and please go ahead.
Okay, well, thank you very much. Hello, everybody, and thank you for attending today's webinar. I'm David Tetley of Elma Electronic, and we're going to kick off the webinar today with Dave Walsh at Parry Labs setting the scene and providing an overview of the importance of MOSA and COTS in US military programs. Then I'm going to talk about using these concepts to architect computer systems via some practical examples. Dave is then going to talk about applying MOSA and COTS to software, and I'll wrap up by showing how the hardware and software come together to build highly configurable, adaptable, and cost-effective solutions. So now I'm going to hand over to Dave. Take it away, Dave.
All right. Hello, everybody. Really excited for today's discussion on, two areas of conversation, topics of conversation that, at the surface, some people think are incongruent, but in reality are very much aligned. So I'll start off with a quick overview of MOSA over the years. And so, really the first major guidance coming out in 2017 under Title 10 requiring MOSA for middle tier acquisitions. That was then later expanded in 2021, really across all of defense, added language around data rights, added implementation details, which led to many different reference architectures being created across the Department of Defense, providing a framework. And you saw this methodical movement coming out of the DoD, providing this Title 10 guidance to then secretaries, providing guidance to the services, OSD or OUSD R&E, providing guidance from architecture and data rights, really thinking about the business and operational outcomes of what MOSA was seeking to achieve at the time. And then that, went into each area for each of the PMs. So you have data rights books, a lot of guidance to acquisition officials to be able to acquire weapon systems and different systems across defense in a modular way, really getting after the 5 pillars of MOSA that I would imagine anyone really dialing into this webinar would already be familiar with. As you look across the aisle and you look at what happened with COTS, it actually predates MOSA. Going back to the Parry memo, which was during the Clinton administration, and it was really this shift out of like Cold War era budgeting, and it was a realization that our commercial technologies had outpaced our defense technologies, and there was a need. If you fast forward to today, a lot can be said the same. There's commercial technologies that are outpacing defense technologies, and there's a need. So that COTS guidance, first starting back in the Clinton administration and now seeing again in this current administration, it's the realization that capability is needed now. So when you merge the two together, really that is a wonderful opportunity to get Defense 2.0 correct. And correct being a subjective term in how I'm using it. What I specifically mean by that is really having MOSA and all the investment that went into the RDT&E, the frameworks that were developed across each of the services, Army, each PEO having, and we'll talk about some of them throughout this presentation, providing guidance that align to standards like FACE and OMS, things across the Air Force with GARA and then AMS-GRA, all those acronyms will be defined. GCIA with POGCS. There's a lot of goodness that happened in building frameworks. And when you overlay COTS on top of that, it's an opportunity to leverage that framework and then have COTS provide the content. Also from a budgeting perspective, there's a lot of RDT&E dollars that were spent in terms of, getting these frameworks correct, and now wanting to move fast and procure COTS technologies. Budgets are changing, and there's an opportunity really to take the architecture that's been invested in, put in commercial content, and then test that framework so that you're able to continue to compete because of the risk of really the COTS alone, driving vendor lock and then decreased capability and decreased best of breed opportunities for many of the defense missions that they'll at first accelerate. So really excited for this discussion. This is really the scene setting of what we're going to talk about in application as we dive into the details. And with that, I'll hand it back over to David Tetley.
Okay, thank you, Dave. So what I'm going to discuss now is open standards hardware architectures based on the Sensor Open System Architecture known as SOSA, which is a technical standard under the umbrella of the Modular Open Systems Approach. I'm going to talk about how systems can be architected using the growing ecosystem of SOSA-aligned hardware via some examples that support different application spaces and host platforms. And I'll discuss some key considerations when architecting these systems, including system and chassis management. So SOSA defines a technical standard from a system perspective, and it tightens up what was a broad OpenVPX specification. The goal of SOSA is to achieve plug and play, where any vendor's cards matching a slot profile can be interchangeable. And from a hardware perspective, though, it extends beyond the plug-in card to the chassis, the backplane, and associated infrastructure, including chassis management, but it also extends into software. And it standardizes some key aspects of the software infrastructure. The runtime environment profiles define the software environment on which SOSA applications must run. The system management section defines the framework for the management of the hardware infrastructure and application modules. The task management section defines the coordination of mission operations. And also the standard defines key services required to support these system operations and management, such as security and network services. So how do we build a system using SOSA components? Well, firstly, you need to determine the functionality you require in your system and ask yourself questions like, what type of data do I need to ingest and at what rate? What are the key outputs for the system? How much processing power do I need? And how does it need to be distributed? And what are my security requirements? And answering these questions then helps you choose the plugin cards or picks that together can satisfy the mission requirements. These picks need hardware infrastructure around them, and firstly, they needed the appropriate interconnect topology to satisfy the required inputs, outputs, and data flow between the picks. And this drives the backplane design, which is at the heart of the system, and ensuring the signal integrity of the connections of the picks and the I/O is key. And here, detailed analysis via simulation is an important aspect of the backplane design. The inclusion of a chassis manager is mandated by SOSA to manage the health of the chassis and other infrastructure within the enclosure, and it's usually required to other infrastructure is usually required within the chassis to consolidate or convert I/O signals to ensure interoperability between the platform and the plugin cards. Then there's the chassis enclosure itself, which houses the picks, the backplane, and the additional infrastructure, and this must meet the environmental requirements for the mission. And this also requires detailed analysis via modeling and simulation to shape the design. One key point to note in all of this is that before jumping into a rugged deployable system design, it's common practice to bring the key picks into a lab development system. And this facilitates performance evaluation, software integration, which is a major step to de-risking the rugged system design. Now let's look at some example use cases, and the first one is a naval electro-optical IR processing system. And this example brings in optical and infrared camera imagery from a camera gimbal, performs some image processing to identify, classify potential targets. It supports an operator console, but also has closed loop control of gimbals. So let's look at the key components in a VPX architecture that may satisfy this application. So firstly, a compute-intensive single-board computer paired with a GPU supporting 3G SDI camera ingest is used to bring in the data, the low latency, and perform the data processing and tracking either through traditional image processing or AI techniques. An I/O-intensive single-board computer manages the human-machine interface and control of the associated gimbals and provides the system housekeeping. A precision time and navigation pick provides locality and time data to the platform. And then at the heart of the system is a high-speed Ethernet switch, which provides communication pathways between these elements and also outside of the chassis to the platform infrastructure. This type of architecture can be scaled to add GPU processing for AI algorithms, for example, and this can be achieved using GPU picks with an onboard PCIe switch, enabling daisy chaining of GPUs. You can also use this feature to add high-speed storage to the system, and this could be important to record live imagery for post-mission analysis or AI training. The next example is an Army mobile signal intelligence application. And here, RF tuner picks are the software radio receivers that provide the signal data to the compute-intensive single-board computers for signal processing. Again, an I/O-intensive single-board computer supports the mission management and the human interfaces. A timing card provides a common low-noise clock for the tuners. And again, at the heart of the system is a 100 gig Ethernet switch. And this is key in providing high bandwidth interconnect topology, supporting RF data transport using the Modular Open Radio Architecture standard known as MOSA. Note in signal intelligence there's a growing trend to use AI for signal classification. And this can be added by pairing one or more of the compute-intensive SBCs with GPU cards. The next example is a radar processor, and modern ASA radars are very processing intensive. So here I'm showing a 6U VPX solution, which has the advantage of supporting higher processing densities and a higher level of system scalability due to the higher pin count. So if we look at the RF ingest, 6U cards can support a higher density of RF channels and large multiple FPGAs for data pre-processing, such as digital down conversion. 6U VPX processing cards can host 2 server-class Intel CPUs or NVIDIA GPUs, each supporting multiple 100 gigabit Ethernet interfaces. And then the latest 6U Ethernet switches can provide a high density of 100 gigabit Ethernet on the data plane, 10 gigabit Ethernet on the control plane, and also provide multiple 100 gig fiber links directly off the card. And this can be really important if the RF analog to digital conversion is being done at the antenna, and the digital IQ data is coming over over optical Ethernet, as it removes the need for expensive media conversion within the chassis. As in the 3U solutions, a single board computer performs the mission management and other housekeeping tasks. So just some architecture notes around this RF ingest. So PCIe has been a key interface for data ingest over the last 15 years, and it often bridges between other standard and legacy protocols to get data into CPU memory for processing. However, it's not a true switch fabric, so it limits its flexibility. And simple point-to-point type ingest architectures are often used, as shown on the left here. PCIe switches supporting partitioning and non-transparent bridging improve the situation, and the switch architecture in the middle, whilst more complex to implement, adds some flexibility, allowing ADC samples to be directed from the FPGA, from either FPGA to either CPU. But a much better approach, and becoming increasingly more common, is to use high-speed Ethernet for your data ingest. And this has been facilitated by 2 key technologies. Firstly, the advent of 40G and now 100G Ethernet in the OpenVPX ecosystem, and also the advent of RDMA technology enabling the data to be moved from the ADCs to the processing elements with very low latencies. And whilst RDMA has been around for CPU to CPU data movement for some time, RDMA capable IP cores for FPGAs have only recently become widely available. But using Ethernet for the IQ data provides a much more scalable and flexible architecture, as the data can be directed to any processing element connected to the switch network, as shown in the diagram on the right. And this enables sort of an overlapping round-robin processing approach, which maximizes your processing efficiency within the system. So the final example I'm going to talk about is a launched effects airborne platform. And here, the new VNX Plus form factor is used due to its lower size, weight, and power, enabling it to be deployed on small platforms where VPX is just not practical. So in this example, again, we have an SBC running the mission software, controlling the avionics IO, which is on a QMC mezzanine in this case. It also manages the RF communications to the command platform via a radio card. A PNT card, again, provides the navigation and timing information. And this example shows a AI sensor processor, which in this example is processing data from multiple camera sensors. The one thing you may have noticed with all these architectures is there are some synergies, and by swapping out one or two PICs and running a different software load, you could switch between applications. You could also furnish the system with all the PICs required to accommodate multiple missions within the same chassis, and missions could then either be switched on the fly or run simultaneously. And in order to support this in a portable manner, SOSA has defined a specification for system and task management to facilitate this reconfigurable computing concept. System management standardizes the management of the health, operation, and configuration of the platform and its security, and it's architected as a series of management services for the system elements, and then managers that oversee and coordinate the management function. An important aspect of system management is chassis management, which manages the hardware within the chassis, and it standardizes the management of the health, operation, and configuration of this hardware. The chassis manager uses what SOSA calls the out-of-band interface, leveraging the VIDA 46.11 IPMI software interface to get health information from the plug-in cards. It also communicates with other sensors in the chassis, such as fans and temperature sensors. And it consolidates this health information, and a management agent provides a standard software interface to the system manager via what's known as the in-band interface, which is an Ethernet interface. So standard software interfaces are fundamental for interoperable, portable, and configurable computing, which is directly relevant to the next section. And now I'm going to hand back to Dave Walsh, who's going to talk about how COTS software is the key to meeting most requirements in a portable, cost-effective way. So hand it back to you, Dave. Take it away.
All right, sounds good. So moving into the next slides, we'll get into COTS software that Parry Labs has invested in to implement different government reference architecture requirements at varying levels across each DoD organization. So quickly, just overlaying, and we'll bring this together in the end. Army Aviation has made a significant investment into a requirement called the Aviation Mission Computing Environment, or AMCE. This really breaks down the hardware requirements that David just walked through, software loading, and then the section that Stradia integrates and implements directly is really the concept of a mission or safety critical software operating environment. So AMC was written, a bunch of different companies came together. It was always an Army Aviation led effort with their certifiers, with the best architects, the best and brightest minds that Army Aviation had, in collaboration with many smart people on the industry side. And so this is part of that investment, going back to the stage setting of where can you leverage MOSA to enable COTS plug and play, so that you're able to meet the hardest and most relevant safety and security challenges and requirements that exist, in the name of trying to get capability to the field. So you don't need to forsake, lethality and survivability for speed and quality. And that's really what AMCE does for Army Aviation. And so, iterative requirement, it went through infrastructure services being built first, things like data logging, data storage, operational load management. It then moves into, what are the zero trust requirements that secure those weapon systems? And so there's requirements for encryption and decryption, digital signatures, and there's 11 different services that exist. And then there's mandates on how you configure your hypervisor or operating system, depending if it's a mission or safety critical system. And so it prevents vendor lock at the RTOS level and hypervisor level, where there's things you can do in memory that now they're enforcing specific interfaces in open standards. You know, the requirement itself wasn't, and this is kind of going back to like why it's so great for COTS. It was really built in commercial standards, and so they had DO297, really the buildup of the software and hardware of DO178, DO254 really coming together and creating modularities that are reusable. And so there's really, you know, 3 different second generation IMAs that follow that DO297 requirement. Those modules that are, you know, instantiated in Stradia, and you know, this is solving again business and operational problems. You know, P-Aviation had and has platforms that you can have the same vendor in 2 different places, and it actually takes more time and more money to integrate an end user capability between one platform and another. And I'll forego the examples because the companies would be obvious, and that's not the point of this presentation. But really this requirement is enabling you to go fast, plug in COTS, and really provide the open interfaces and modularity that allow you to continue to go fast and compete. If you go to the ground side, POGCS was doing something very similar. They also leverage FACE, which I should have said on the MCE. You know, so it's a FACE-based data architecture. In software, they had their own services and common data services. They broke down, you know, differences in types of compute in that reference architecture between crew station and common computing. They leverage requirements like TSN, which so did P-Aviation. So a lot of similarities between the 2 reference architectures. And you know, they're hitting a lot of the same types of interfaces, capabilities, modularity, a lot of the same business outcomes and operational outcomes across air and ground with Army. And so what Parry Labs is, we created, you know, a COTS version of that MOSA so that you again can implement immediately the, you know, the infrastructure and cybersecurity services, and then we've added other features on top of that, which we'll talk about later in this section. So, you know, again, going back to FACE, you know, taking this, you know, more of like a high-level marketing slide, which is appropriate for a webinar. And you know, outside of this webinar, happy to get as in detailed as it makes sense in the conversation. But you know, this is just an example of how Stradia on the mission critical side, you know, there could be a safety critical version of this, implements the different segments that exist in FACE, breaking down the OSS and IMOSS, PSSS, TSS, PCS. And really enabling the plug and play architecture and using the FACE technical standard as the medium to do that. There's a number of Army aviation and Army ground programs. There's a number of even Air Force programs that are using this for their safety critical functions on platform. And so, you know, this is a great layer going on top of what David just walked through in many of his examples, and we'll get into some specific examples in his next section. Moving to the Air Force and Navy implementation, you know, really the Air Force led the charge here. They had you know, a very classified reference architecture that's no longer classified. And then they had really this more legacy fleet modernization focused architecture that was led out of the Air Force Lifecycle Management Center and the Open Architecture Management Office. And lots of really smart people on the Air Force side spent time really aligning capability reference architectures, taking their investment in OMS and UCI as really their digital backbone for data, and then aligning different pillars of investment in architecture focused on EW with Big Iron, AP&T with Reggie, you know, Corp with radars, and being able to create a, you know, capability focused approach to being able to bring together complex weapon systems that, again, were developed in different silos across the Air Force. Secretary Kendall reorganized the Air Force around this concept of capabilities first and then applying them to platforms, you know, tying back into that, some of the acquisition things that have changed. So fast forward to, you know, going from years of GAR development into now pivoting AMS GRA, and obviously, you know, being opaque because of the, you know, there is COI data that's involved in handling that information. They start to address things like cyber and infrastructure and how you partition your architectures like AMC did. So, you know, getting away from really using OMS as this middleware and having different capability reference architectures tied together, now they're getting into, well, how do you actually implement them on platform? You know, and so Stradia in this version does that. The Navy, and we're seeing requirements aligning with AMS GRA from the Navy, is leveraging that investment in both advancing what was used out of GARA and now being pulled forward into AMS-GRA. So again, for Stradia, this is a breakdown of, all right, well, before it was space, and now the architecture that's being used is really OMS UCI. They have another concept within AMS as well that it implements, but intentionally not showing on this graphic. But this is, again, just the alignment, again, looking at why it's important to use these well-defined open interfaces that anybody can plug into, whether that's FACE or, in this case, OMS. So what Parry Labs has continued to do is really add on top of that in areas that make sense for infrastructure, and looking at the requirements as what are the needs of the warfighter and what does our infrastructure need to provide. And this gets into why COTS aligned to MOSA makes sense. Over-the-air updates, secure over-the-air updates is something that doesn't really exist in many requirements. It's hit or miss. There's not strong technical requirements around that, and so Parry Labs has leaned forward into really investing in post-quantum encrypted over-the-air updates. Software-defined networking and SD-WAN are both capabilities so that you have the ability to now not just securely push things from cloud to edge and edge to edge, but in a contested environment or denied environment, having the ability to maintain those data links and having auto pace, going from a primary, alternate, contingency, and emergency frequency, and switching over, whether that's an external network or internal network on platform. And so again, not strong requirements exist across the DoD, and so providing instantiations and being able to support third-party software. There's a number of SD-WAN providers that we've integrated into Stradia versus just the version that comes with it. Zero trust is a requirement that really, from an enterprise IT systems perspective, is a 2027 requirement. This current Secretary of Defense pushed that to 2035 for weapon systems. Well, Parry Labs has been investing in that for some time now, and so really the push going to the end of this year is, well, how can you align and implement all the concepts in the zero trust, the DoD CIO's reference architecture tied to the 7 pillars that exist for zero trust, and so that's being implemented this year in Stradia. And then the last is with the onset of AI. There's a lot of talks about MLOps or AI to edge and people using GPUs. There is much in the same way that DeepSeek provided different levels of efficiency. What Parry Labs is providing is many different open APIs that exist in the AI world brought to the edge and right size for the edge processors so that you can add in many different capabilities, not just autonomy, or many different people's autonomy, and have them communicate using either agentic or generative AI. And so keeping up with the times, taking the investments from the commercial industry, which is heavily investing in AI, clearly, if anyone reads the news or is using it themselves, and not, again, throwing away all the safety, all the security, all the interoperability, and being able to plug in, again, COTS AI applications and making weapon systems and defense systems more effective at accomplishing their mission. So add those together as infrastructure, and then you start to add really and build a Defense 2.0 app store. And so, we've been doing this at Parry Labs for some time, really integrating capabilities, and now it's doing it on top of these different reference architectures and really driving what is the Defense 2.0 app store. So being able to plug and play, whether it's AITR and autonomy, hardware and design, working with folks like Elma, EW and spectrum management, network management, et cetera, going across the different categories here, and being able to just actually plug and play capabilities. What that looks like is, really having an end user configurable UI to be able to configure and reconfigure partitions, hypervisors, and containers. So dragging and dropping COTS software or GOT software into the right partitions, and then connecting over these well-established open interfaces that these different reference architectures provide as a framework. Being able to manage and connect over a secure over-the-air update, and then be able to dynamically manage utilization both on platform and waveforms that are connected to that system over those different SDN and SD-WAN connections. That's all great for the edge. The other part of this is, as we look to align COTS and MOSA, is how do you start to really drive integration to the left and not require all the hardware that exists, start to leverage the cloud, not in the same way that the commercial industry does, but again, now for defense systems. And so another COTS product that is bringing together hardware and software that Parry Labs develops is called the Virtual Integration Workspace. And so this platform really allows users to log in, select their hardware. They can build that in real time, much like you would at any type of Apple or Dell store, where you're selecting the types of processing, whether that's x86 GPU or ARM, selecting your RAM, your I/O, dropping in your capabilities, and then deploying that and actually looking at the utilization and providing access to third parties. And so now, again, doing those digital integrations, working with folks like Elma to be able to bring together these designs and interact with them early ahead of really the hardware being available and being able to right-size capabilities. And tying it back to the last slide that I really have is, bringing that Defense 2.0 marketplace. And so really the view having a marketplace to pull in, the SOSA hardware that Elma just talked through, the right GRAs in software tied to these different complex requirements, and then pulling in many different third-party software. And so that is another capability that, combined between Elma and Parry Labs, we're able to provide, where COTS and MOSA are coming together, really providing a framework and ecosystem to leverage all the investment in MOSA, accelerate the use of COTS and the competition for speed, and really meet the needs that our warfighters really need today. So with that, I'll hand it back to David Tetley. May chime in a couple times. I'm really looking forward to the Q&A at the end of the session. David, back to you.
Thank you very much, Dave. So what I'm going to now talk about is how is really bringing what you've heard about the open standards based hardware and the MOSA COTS software that Dave's discussed, and bringing it together to show how a software stack such as Stratia can combine with hardware to create scalable, portable, and interoperable computer systems using MOSA. And when this is coupled with system management, task management, and supporting services, systems can become software defined, supporting multiple missions based on software and firmware load. So Stratia provides the core software stack that will run, and it will run on any of the single board computers you saw in the architecture examples. The SOSA management, system management and services modules can be integrated into this stack and complement the Stratia services to support SOSA aligned application modules. And the containerized applications can sit in a local application store and deployed on the computer elements using the container management layer, which provides container orchestration. That's how it sort of all fits together. And now if we take a look at it in the context of three of the examples I showed, starting with the naval electro-optical IR platform. Here, the Stratia Air and Sea variant would be most applicable, supporting the Agile Mission System Government Reference Architecture, AMS-GRA. Hope I've got that right, Dave. And this supports capability interfaces and reference architectures such as OMS for sensor mission systems, Big Iron for electronic warfare, and Reggie for precision time and navigation. And Dave, I don't know if you want to add anything to that.
Yeah, I mean, I think the great part about this is that if there's investments being made that are following, whether it's OMS or Big Iron or Reggie or FACE, really what this also provides is the ability for portability and reusability of capabilities across platforms using that same framework. And so in the case of the Navy and really trying to get after speed and capability for, any platform using AMS-GRA, this is an opportunity now to get reuse and speed. That'd be the thing I'd add to this one. Okay,
thank you. And then so the next one is the SIGINT platform example, and this is where Stratia Ground would be the most applicable, supporting the Ground Combat System Common Infrastructure Architecture (GCIA) and its associated services, and additional capability interfaces and reference architectures such as the common data services, crew station computing services, and common computing services. And again, Dave, I'll let you elaborate on that.
Yeah, sure. I mean, I think in this case, what's great is that GCIA, because it's a direct and really instantiation of that requirement, is you're getting, instant separation of concerns, how you manage mission versus safety critical systems. You're able to quickly apply the appropriate logical architecture and use the right interfaces and APIs across, different types of processing across the common, the crew station and common compute that exists within the GCI standard. And so again, this really gets after, in the ground community's eyes, giving the right modularity and speed and rigor around many different software and hardware components that plug into the architecture.
And then finally, we've got the launch effects vehicle mission computer. And this is where the Stradia Aviation variant could be applicable based on the Aviation Mission Computing Environment, AMCE. And in this example, we've got a hypervisor, which is used to support safety critical partitioning, potentially running a hybrid of two OSs here. Here, the face TSSS translation capabilities of Stradia can play an important role, along with additional infrastructure services, such as and the zero trust infrastructure, and also the over-the-air updates. And again, Dave, I'll let you jump in there if you've got anything to add.
Yeah, I mean, I think this is a great example of where you can have both a safety or mission critical implementation in software on something small like this VNX chassis that's being shown, VNX Plus chassis. And so I think it's great because you're showing the ability to handle safety critical concerns. And I always just take the opportunity, looking at the example that you chose here, David, like there's going to be thousands of launched effects or UAS that are going to be autonomously flying around manned aircraft and soldiers at different points on a battlefield. The ability to add capability in hardware quickly, capability in software quickly, and be able to do that using both safety critical and mission critical software that supports the different hardware use cases that these operations will require, I think is very powerful. And I think this is a great slide to end on, showing how, and this version, AMCE with Army Aviation, is enabling that.
Thank you. Yeah. So let's just finish with the key takeaways. And firstly, we've learned that the MOSA enables adaptability of computer systems to multiple mission types across a range of Army, Navy, and Air Force platforms. And this adaptability enables reuse, simplifies technology refresh, and greatly reduces costs throughout the acquisition lifecycle of a program. The SOSA technical standard facilitates interoperability and portability at the plug-in card level. The use of a digital twin via a virtual integration workspace can significantly de-risk software development and accelerate deployment. But overall, the combination of COTS software such as Stratia and SOSA hardware can truly could create truly application-ready deployable platforms. I think that's really the key message of today. And that concludes the presentation. Thank you for listening. I'll hand over to our hosts at Military Embedded Systems.
Perfect. Thank you so much for your presentation and for your insights. We've got some questions already, so we'll jump right into them. Okay. Given the technical feasibility of integrating plug-in cards, and maybe from multiple vendors, under the MOSA framework to build modular radar systems, what impact might this have on the traditional role of large prime contractors like Raytheon or Thales?
Well, I'll take that. I mean, I think those large integrators, they really bring their value with the application expertise and the integration of the platform as a whole. The ability in the likes of Elma have are able to de-risk by dealing with the sort of lower level of integration of the plugin cards and the base layer of software, but the application capability really comes from those guys. So yeah, that's my perspective.
Thank you very much. Okay. What are some of the pitfalls that you gentlemen might see if COTS is used without using the GRAs that you referenced in your presentations?
Yep. Yeah, I can take that one. I mean, really it's going back to the frameworks that MOSA provides. It's enforcing, the widely adopted and typically government-owned interfaces. And the reason why that's important, if you look at a lot of the Title 10 requirements, is that those interfaces are tying into modules. If you don't have that framework, well, then that module is defined purely by industry, and they're incentivized, and it's a simpler architecture when you're designing for yourself, your own concerns as a company, to use proprietary SDKs, to use proprietary interfaces that make it easier for you to have efficiencies inside of your own vertically integrated software solution. And so, I think the pitfalls is that if you throw away MOSA and you just adopt different proprietary SDKs that tie into one vendor solution, you're immediately eliminating competition. You gain efficiency with that one vendor, but you're blocking out all the long line of vendors that will continue to invest and innovate. And you'll have a really hard time getting back to the best of breed, right? And I think that's why you saw COTS. Like there's a number of named examples you could work through, but I think the pitfall is going fully COTS and ignoring MOSA. Will eventually lead to probably MOSA 2.0. And I think we have an opportunity to get Defense 2.0 correct by just combining the two now.
Excellent, thank you. Could you talk through how ruggedization and militarization is addressed using MOSA? The question asker cites MIL 810 and ATPD 2404 compliance as examples.
Well, I guess standards under the MOSA umbrella really are addressing this, and SOSA, for example, is addressing this by working with VITA and VITA 47 is a standard that's SOSA points to that encapsulates ruggedization requirements at a LRU level, effectively a chassis level. So that's how it's really being addressed by the standards under the umbrella of MOSA. That's how I see it.
Thank you. Have either of you seen much demand for the Victory open system standard for land mobile systems?
Yeah, I mean, if you look at GCIA as a requirement, Victory is referenced directly inside of GCIA, and so I think pulling together some of the hardware requirements that exist as part of that reference architecture coming in at PEO GCS, yes, right. I think that's one of the things with the GRAs, like just not for those that have not read those different reference architectures across the DoD. It's bringing together standards like FACE and SOSA, and HOST and CMOS, and creating a lot of really implementation requirements that you reference off of to be able to build these systems. And so Victory is very much part of that in terms of integrating onto the vehicle platforms themselves. David, if you have anything to add to that. Yeah.
We see, well, Victory conformance is a requirement that is often flowed down to the system level, and there are a number of many switches in the SOSA ecosystem and rugged package products that sort of fit under the MOSA umbrella that are Victory compliant. So yeah, it's widely used.
Okay, we're seeing a lot of VPX hardware COTS solutions with MOSA. Somebody's curious, could CPCI serial COTS solutions also be capable of supporting that standard?
So, I mean, CPCI serial is still used in many military applications. I mean, it doesn't fit under the SOSA umbrella. It's not a standard called out by SOSA, but it's a modular form factor. So could effectively sits under the MOSA umbrella, and it's suitable for some types of some application spaces. Generally, there's a smaller ecosystem and different capabilities of compact PCIe serial plug-in cards, but yeah, it has its place in the MOSA ecosystem, I think.
Excellent, thank you. When will VNX Plus products start becoming widely available?
So yeah, I mean, so VNX Plus, I mean, it's a very new standard, but there was the previous Vita standard that was just VNX, and there's a lot of VNX Plus cards available on the market, and VNX Plus cards are starting to hit the market and have been in the last couple of years, but the ecosystem really isn't strong yet. But what we're expecting is it to really strengthen up in the next sort of 12 to 18 months, because we know a lot of vendors are working on plug-in card solutions, from single board computers to switches and radio cards. So it's coming, and I think we look ahead in 6 months, you're going to see a portfolio of an ecosystem of cards that will help you architect some pretty compelling systems.
Thank you. Okay, how mature is the small form factor COTS solutions presented here using PNT and communications as an example?
I mean, so VPX has been around for many years. So VNX solutions VPX solutions and 3U VPX is now very mature. There's lots of different PNT VPX solutions available in the ecosystem, some of which are SOSA aligned. So I will say, yeah, it's now a mature technology for sure.
Okay, what challenges are you foreseeing in integrating legacy subsystems into a MOSA aligned architecture, particularly in airborne and maritime platforms?
Yeah, I mean, I think the biggest barrier is using the reference architectures we talked about in this presentation. There's a lot of solicitations that come out, and problems could be solved integrating legacy sensors because there are data concentrators, or the concept of a data concentrator in every reference architecture that can bring in legacy IO, bring it to something more Ethernet based, and then really get to the more software defined weapon systems that David talked about when you bring the two together. And so I think the number one barrier to doing modernization correctly is to understand that these GRAs are there to set the stage, solve the problems, and also align those legacy platforms with where the next gen, both maritime and aviation platforms are heading.
Right. And some of the SOSA runtime environment profiles address the ability to bring legacy applications into an open standard by being able to wrap up that capability in a containerized module, right? And so that's an important aspect. The hardware, there's these can be challenging, but FPGAs that convert legacy interfaces into more standard interfaces, are often now a solution to adapting legacy into the VPX and the VNX Plus type architectures.
All right, thank you both. And when architecting a VPX system, how do you determine the ordering and arrangement of the cards in the slots?
Yeah, it depends on a number of factors, and firstly, you're dealing with some pretty high-speed signals. For example, on data plane signals, you're looking at 25 gigabits per second on a communication lane. So you want to keep those below a certain length. You don't want to transmit. You don't want a signal of that speed going across 12 slots. So you tend to put consolidate your switch cards that have a lot of these high-speed signals coming from the plug-in cards in the middle. And also then you want your I/O cards near where the I/O connectors are, where the I/O panel is. So this potentially minimizes EMI issues. But also there's a thermal consideration. You want to sort of make sure that you don't have hotspots in your chassis by grouping all the hot cards in within a couple of slots, and you want to try and distribute that evenly, or stack the hotter cards closer to where the fan is in a convection conduction cool design. So a number of different factors there at play.
Awesome, thanks. We are coming up on the top of the hour here, so we're going to wrap up shortly. But we got another question for you. What are the challenges in implementing RDMA over 100G in an FPGA?
Okay, so so as I mentioned in my talk, IP RDMA capable IP cores are now sort of much more widely available, but integrating them into the FPGA is still a challenge. It's effectively a plumbing task where you need to sort of ensure the data flow from your ADCs into the RDMA MAC can keep up with the data rates required and stream seamlessly over your RDMA capable link. And normally to do this, you use what's called connectionless RDMA, which is the RDMA equivalent of UDP. And that removes the need for handshaking, reduces the initial latency, and sort of simplifies the software solution. So those are some key considerations there.
All right, thank you so much. And time for a quick comment, not a question. But an audience member would like to say thank you for the presentation and said it was informative and thorough, and I would like to echo their comments as well. And I'm afraid we are out of time for those questions we did not have time to answer. We will be getting back to you via email. And that concludes today's presentation. On behalf of Military and Aerospace Electronics, I'd like to thank David Tetley and Dave Walsh for joining us today, and Elma for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of your day.
Thank you.